Okay, so this is my deer in the headlight moment. So this is the kudu that I was lucky to see, and it means a lot to me because that's actually my name. My name is Li Wenxi. So Li Wen means, Li means in the Chinese character is a deer with huge antelope. So that's just like me. Then Wen means writing and pattern and veins on silk. Okay, so it's a pretty pattern. So you see the pretty pattern on the stripe? Okay, so I feel like that's me. So I saw this kudu in this park in a very brief moment that we crossed the path. So I kind of feel like I'm that kudu for you. So I would like to tell you the story of where I'm from and where I'm heading. And so that this morning we're just sharing the journey. So hopefully in this journey, I have met a lot of angels and my lucky stars, and that's the reason that I'm here today. From a coal miner's bookkeeper's daughter, and so on the way I have helped a lot of students, and they are very sweet to me. So I have students that I talked to 30-some years ago. Even the person that took me to the airport is also my student. So I appreciate all this good fortune I have, and I hope that I will build and enlarge this Chpc quantum AI family with you all, and we'll continue this journey. Through this presentation, I'll be proposing a lot of ideas, and I've been talking too much over the word, but I was in Japan talking just like this, and in India and stuff. But I would like to really sit down and do real work, and hope each of you will kind of find common ground to collaborate with me. I have a lot of ideas for many lifetimes. Okay, so happy. Yeah, so we met at the SC23 and then also the year before. So we're lucky to go to NCAR to check the climate, and then that is Dr. Group of NCSA. He's the one giving out all the awards. So this is the NCAR. So I was talking to the people, researcher there, and I know that climate is a very important issue close to heart to everybody here. Also, I'm from Houston, and Houston is sinking to the ocean. We don't want that to happen, right? So also I need a lot of help on that. But I feel that if anything that you want to take away from this talk is, I would like to encourage each one of us to be proactive in everything. I'm a little future-oriented, so I don't fit in anywhere. However, I think proactive is a key. Prevention is a key, right? So they say we use billions of dollars, try to check the environment, and then try to mitigate the situation. Can we use that majority of the $1 billion to try to create a good environment, right? And create health, instead of trying to spend all the money on checkup. So this is what I encourage. I hope that Houston is the place where all the king and queen will go to the biggest medical center. But I'm not so proud of it. I want Houston to be the healthy city. And I hope that I will be the one that to help, and I hope I need your help. So this is, again, some picture of the NCAR. It's a tour guide here. Beautiful building and scenery. So this is the, Iron Pei is the architect, and then we have a nice meal together. Okay, so the world is going from this different paradigm shift, and where are we, right? So again, I'm saying I'm a little future-oriented. So we have the experiments. Before we have a lot of like genius like Einstein and Feynman and different people, they have this model, Newton, they have this model in their mind, and then they don't have data enough to prove it. So we have to design experiment to collect the data to verify the model. And then after that, we have computers, so we create a lot of simulations. and then generate the different Monte Carlo and different things. And then let me go back to that. Okay, so then we have the computational from empirical, theoretical to computational, and now we are in the data-centric, data-intensive era. So what is next? It could be quantum AI. So many years ago, they say every 4 days the data in the world doubles. So okay, here is a beautiful mind, right? So we're in a very strange period of time that we didn't have computer. We were walking in the jungle, and then all of a sudden, everybody has a personal computer. We have electricity at home and all this kind of thing. And then gradually, the computer gets smaller and smaller and go into the cloud. And I heard the iPin is coming. So for $700, you have a pin, and then it will be like your cell phone. So A Beautiful Mind is a movie. It was not going to be very shocking when you watch the movie anymore, because nowadays everybody's talking to themselves, right? And they all have imaginary friends, right? So when you're at home, you're calling on the phone, and then people say the dog and cats keep talking because they thought there's nobody else here. You're talking to me, right? So this is the my quantum computing, a quantum mechanic professor. She is from Oxford, Dr. McDermott, and there's an Einstein picture there. So for the classical physics people, they don't like quantum computing and quantum phenomena, quantum mechanics too much because they are a little bit overtrained. When it's the classical mechanics, it's kind of very strange to have the superposition, entanglement, and those kind of things. However, for me, I do not have very strong physics background, so quantum is very natural for me. Okay, actually, classical mechanics is not that natural to me. So I'm running. So where my arms going, forward or backward, right? So I'm very lucky to have the best professor, and she actually told me I'm the best student. Her husband actually is the father of handedness. Okay, so they are developing the chirality quantum mechanics. Hopefully we'll hear that they get the Nobel Prize next. Okay, so this is my picture. I had to make a profile when I was visiting Lawrence Berkeley Lab. And over there you can see the IBM quantum markup. There's a one tiered chandelier. So now they have 3. Okay, so that's just 2-3 years later. Oh, this is where my parents, okay. I thank Oak Ridge National Lab that I visited last year, and I thank Texas, because if it's not because of Texas oil, my father will be done at World War II, won't come home and have 6 kids. And I'm the little baby right there. Okay, so this is where I'm from. I was running to a first year of computer engineering program. So can you spot a little girl there? Okay. So all my friends, they are all making chips in Taiwan, so I was made in Taiwan. So right now, I'm in University of Houston, Clear Lake, right on Johnson Space Center, NASA campus. And we have 250 acres of wild land preserved. So we're very lucky to be in a nature area. So this is some of the pictures that I took. So I'm very lucky. And so this is a building that I work. The gentleman there is a quantum engineer. He's from Golden, Colorado, and he met me in a conference like this, and he's been following me, so I've been a mentor for him. Okay, so this is we're right by NASA Space Center, Houston. So this is kind of like my bio overview there. So you can see the picture of SC-15 and Summit, which was the last fastest supercomputer like 2 times ago. So 2015, I submit a poster to SC, and I got 3 reviews, okay? So the first review that I really like, so I'm just trying to tell you, maybe you are the reviewer and I thank you, and it says my idea is very unusual and extraordinary. It's gonna be a game changer. The second person said, well, it looked like a good one, but it's not my field. I'm not that interested. And the third one said, what is quantum computing and why do I have to know it? Now, to get to supercomputing conference acceptance, you have to have 3 votes out of 3, okay? So I didn't get voted there. However, the Future Technology Conference was very kind to me, and they actually giving exception to have me give 2 talks. When I got there in Vancouver, it was very unusual because usually Future Technology Conference is in San Francisco, in the Bay Area. But I don't know, because of the politics, it's hard to get visa, so that year was in Canada. It was only 7 miles away from D-Wave, so I got a great tour right there. When I got there, I realized I was the first speaker of the first 2 papers, opening of the conference, and I had to speak after Peter Mueller of IBM Quantum, and you know who the person is that's next to it? John Martinez. So he is the professor that delivered the Google quantum supremacy. So about a year and a half later after this picture was taken, and at that conference, before my talk, he spoke about how a good quality qubit he's trying to develop. So I'm very proud of him. This is kind of the overview of my talk or my current #1 research there. Although I do a lot of other health, other kind of optimization, like functional health and environment. But over here, I'm trying to integrate the quantum annealing optimization and high-performance computing together. So on the left there, you can see the problem we are solving is earthquake like cybershake. I was able to use my techniques to improve 35% faster. Next one is I'm trying to work on the Chpc conjugated gradient. That one, the current fastest performance is by Fugaku, 16 petaflop, by Frontier, 14 petaflop, and by NEC system, 1 petaflop. Now, for the percentage of the peak performance is 3%, 0.8%, and 6%. Now, 2015, there will be NEC, they did the vector computing for 10% peak performance. That means that Frontier is 1.5 exaflop, but only can perform Chpc conjugated gradient benchmark with 14 petaflop, which is 0.8% of the peak performance. And that's where we're gonna try to improve, see if we can do anything about it. And I do space radiation, AMR is another adaptive mesh refinement, robot elbow machine learning, 3D, or hyper Sudoku, mega Sudoku, and the routing problem. So on the right here, the system we're looking at is Frontier Delta at the NCSA, which is similar to the little twin brother of the Frontier. They are in the Dragonfly topology. That's where I'm focusing on the topology of the processor nodes. They use dynamic also slingshot. So typically, Dragonfly is 3 hops between nodes. However, in reality, going from one task, passing data to another, the data movement can cause, maybe even hundreds of hops across the system. Next system we're looking at is Fugaku at RIKEN. I had the chance to visit Fugaku because I was keynote speaker in Osaka this summer. All right, so Blue Waters is the system I use to optimize for the CyberShake project at NCSA, which is a 3D torus Fugaku is the tofu fusion, so which is it's got a 3D torus plus the 2D ring inside each cube of 8 processors. So it's a fusion of the ring and the torus cube. Okay. So also Frontera is the tag, so tag is also interested. And then I'm looking also at the NEC vector, as I said, that they have very high percentage peak performance for the system. So what I'm trying to do is trying to find a way to quantum refactor, quantum partition, quantum schedule, and quantum sampling to accelerate HPC computation, okay? In the quantum refactoring means that you have a sequence of instructions, so you just try to find a permutation that is going to produce the highest hit ratio for memory access and fastest execution. Usually, but just by doing the traveling salesman's permutation, you can get about 15–20% faster by out-of-order execution. The second approach is to partition. So I take a software task graph. So right now it's a functional level. So you take your workflow of your functional workflow of your computation, and then I hope to be able to automatically partition into parallel threads. Each thread that is sent to a worker. And these workers are connected together. They are good friends. Okay, they are close by. They are direct connection. So if I have a task and I do the next task, so I do not have to transmit data, it's 0 hop. Now I get a little bit too busy, so I send it to Happy or to one of you. My direct friend, direct neighbor, then it's 1 hop. So 40% of the time will be 0 hop, 50% of the time will be 1 hop, so 90% of the time will be 0.5 hop. So that's my hope that I can make all the data movement to 0.5 hops, and they will be really saving the time and the energy for the computation. So all the computation is actually taking 20% of the global energy, so we can try to cut. And the reason I'm sold by the quantum is because of the energy and other things that I will be explaining. So the reviewer once says an extraordinary perspective, potential to be a game changer to HPC community. And of course, that's the only review that I remember, right? Okay, and if you are the one that wrote the review, I thank you. And I would like you to do the same in your review and to encourage new ideas. Also, I had the pleasure to visit Dr. Satoshi-san at the RICON at the Kobe. Again, I was lucky because I was keynote speaker in Osaka for the Global Expert Conference on AI and robotics, and it happened to be only like maybe 20 minutes to Kobe. So I was very lucky. When I was in Vancouver, I get to visit D-Wave, and when I was in Osaka, I get to visit the So you can see in the blue here is the earthquake protection spring, and then behind is actually there are some black rubber drums, and also this is to cushion when there's earthquake. Over here, this is the team that are also from visiting from Tokyo to Osaka and Kobe to meet me. Those are the quantum hybrid group in the RICON Center. So this is the system that typically, right now, is about 2 tennis court field for the regular, all this big system, Frontier and Fugaku. 2 tennis courts, right? Remember that number? This is the tofu, so that's what I was talking about. There's a ring in the cube, and then there's a torus topology. So I need to learn all this to be able to try to optimize. That is Dr. Satoshi-san. And one of the members was Zoom with us when I was in Kobe, so I get to meet him in person finally. Dr. Satoshi-san actually won the Quay Award in the ISC last year, 2022, at Hamburg, Germany. So latency is not an option because it costs money and execution time. So we try to optimize for each user the number of cores used in the cluster, and the nodes are close by, so there will be minimal hops. So there will be minimize the cost of the charging of the supercomputing time. And if everybody has a local sub-network, then will be less cross-traffic for the center and make the system more efficient. So the first point that I would like to make a case for topology and location and job placement importance is the wave situation. So this is a space radiation code that we were working on to optimize on the Ranger cluster of TAC, Texas Advanced Computing Center. You can see as the number of cores increase, the execution time going down. However, if you go across 16 core to the next board, then it jump up. Okay, and then you go down again, and then 32 core, it jump up. Because there's some kind of communication latency between boards. I guess that's why we're coming to see the wafer scale supercomputer, where all the little pieces of die on the wafer is all together to make a supercomputer. I belong to a group. I was the number 5th campus champion in Texas for the entire United States. Right now, they probably have like maybe 400 plus people. We are the people network that promote the supercomputing called XSEDE, XSEDE, Extreme Science Engineering Discovery Environment. And so I'm in the middle right there. So I don't know if you can see it. Okay. So I was very lucky to be the campus champion because I taught parallel computing since 1989. 1989. Okay, so over there, the downtown CEO, I'm with all these giants. So now every 10 years, they change names. So X, TeraGrid, XSEDE, now it's called XS, NSF XS. So downtown, the two giants around me. So I was I'm the sandwich. So I get to be the first campus champion. I was assigned to world champion biggest earthquake project. On the other side, besides Downtown, is a PI for Exas. The other person is Thomas. Thomas Maiden is the one that organized all the training. So I host the training like every month for MPI, OpenMP, OpenACC, and Big Data Machine Learning. I was lucky to be with Southern California Earthquake Center. This was in Chicago, 2012, 2013. This is the Earthquake Center, so we are doing the largest computation. At the end of my internship or my fellowship that year in 2013, I was able to actually get on board off the bench and do some work. I stood in the giant of Yao Ming and little girl make a slam dunk because I was in the topology area and they have optimized. The world champion team already optimized everything and they don't know what else to optimize. So my collaborator, Dr. Ethan Cui, one of the authors of the CyberShare code, AWP-OCT code, he actually told me to look into the optimization. So I asked the NCSA people to show me when I submit a job, what are the nodes that are assigned to job? How my job is placed on the cluster. So they sent me this. Then I discovered there's a lot of network fragmentation. Luckily, we were able to be the exclusive user that July of 2013 because they were upgrading the system, putting in more nodes. So I was able to study the architecture and realize the Z direction has the highest bandwidth. So I designed a loaf shape to mimic California Earth. And then we were able to improve 35% faster with the yellow portion, which is the torus, actually connect together. So it's one piece of bread, like loft. So then I was able to improve 35% and improve the efficiency to 81%. What does this mean? To run a California earthquake map released every 5 years, just to run one map, maybe more different model, at least 4 different models they have to go through. You have to, the computation electricity just by core hours on the processor, it will cost $850,000 for the electricity. Fugaku is costing $1 billion, Fugaku is $1 billion. It's $14 million electricity. I think Frontier is probably $27 million electricity a year. So there's a lot of electricity over there. Okay, so 35% faster is about $285,000 that I was able to save. I was having fun. I had to give the award speech for 7 minutes. Over there, I have 200 slides. I become very famous on many slides. So this is one of my slides. I was having fun. We have to use a quiz, a pick note script, and then we have to use the Tupperware to be able to allocate the particular note for our operation. So I put the Tupperware there. The picture over there of Blue Waters is the cluster name for the NCSA, but that's a picture I took at Galapagos. It's beautiful blue water. Okay, so this is my design. It's a self-organized, low imbalance. So I do everything opposite, right? Not low balancing, I do low imbalance. Algorithm-specific topology aware, custom topology. I'm designing a specific shape for your application. Latency adaptive, so job placement, heterogeneous. Now I'm looking into automatic composable hardware, so partition for the migration code for the composable hardware. Now, in the dynamic part, it's a little bit more complicated. Slingshot is doing a good job, so if they do any better, I might lose my point. However, Slingshot, it could be also optimized by quantum optimization, as I described. So California is very appreciative, so they send me head and T-shirts, and it says, with all your faults, we still love you, California, because all this, the fault for the earthquake. Okay, so this is, so 2017, I optimized it 2013, 2017. Cybershare code was the golden bell price used by Chinese in the Sunray system. Okay, so the problem is we're getting bigger and bigger data warehouse. So in Houston, we have BP's largest commercial data warehouse. Over here, you have, it's 4 football fields. It's 1990, 25 years ago. This one is only 32 teraflop, okay? So this is now the NEC. So we are able to connect with NEC. They're very interested in, so we met. They came actually to Osaka from Tokyo to meet me, the team in digital vector annealing. And also, we were able to meet, they came to Clear Lake, where I teach. And then also, this time in SC, they invited me to the Brown Palace, beautiful hotel over there. In ISC, I was able to witness the Turing Award winner, Jack Dangaret, and he's going to help us with the conjugated gradient benchmark, because he's a Limpac fan. And then over there, there's Johntown, again, is an XSPI. Over there is Frontier, got the top 500 system award last June. So it's 2022. Not only that, it's $600 million, much cheaper than Fugaku, the previous champion, and it's also the most energy efficient. So I'm very impressed with the HPE. And HPE in April just relocated to make headquarters in Houston, okay? So it's about an hour north of where I live. Over here, this is the D-Wave people, and that is my boss at the he's the ISC General Chair, Dr. John Schaff, and he just snatched one of my students as his employee. Okay, so 2013 is the SC again, because the SC is the first time I get to hold the waffle for the D wave. And Colin Williams gave a talk, and he is actually the most influential person there to make a adiabatic system and the D wave, to shape the D wave direction. So in the adiabatic system, we're doing the quantum annealing. It's an analog system. Basically, you do the annealing process. At the end, you want to settle down to the lowest energy. To be able to do that, you have to have the lowest temperature. So 10 years ago, it was 512 bits called D-Wave 2 system, but the configuration is similar still. It's still the upside down wedding cake, and then it's still about 9 by 9 by 15 refrigerator. This is one of the problems, Charlie Sussman problem, as I just mentioned. And so one of the football player, John also, he just want to study to be a math PhD at MIT. He doesn't want to play football because it's so much fun. But with the quantum, you're able to do it in a blink of eye. So it's about 20 milliseconds or 100 milliseconds here, I said. But it's not 10 to the 58 years to be able to do the computation for that. Somehow, because I'm good at talking about my concept, the whole D-Wave team came visit me. So this is Mark, he's with D-Wave, so the whole D-Wave team came visit me in 2016. 2017, I visited D-Wave, but they came to me before that. So that's the president of D-Wave and the vice president of D-Wave, the president of the D-Wave government, and then Mark is the one. Mark Fortuny gave a talk over there. So I told the team, I said, why are you coming to see me? I don't have a big lab. I'm using the national lab on cloud. And they said, well, we just want to come spend time with me. And I said, okay, give me all your exact spelling of your driver license. And I said, well, so I can get you to see the mission control to the moon, in the NASA. And this is make your trip worthwhile. And they replied, say, oh, we are a small company. We have small budget. We want to focus all our time with you. I was like, you nuts? Anyway, and at that time, why did they come? Because they say in the presentation, we are a small company. We only deal with 3 problems: sampling, optimization, and maybe the factoring. And I say, no, there are like 12,000 people here in SC. I can make everyone your customer if I can optimize the workflow of Chpc with quantum. This year is at least 14 to 17,000 in SC attendance. Now, then I gave many talks in different places, but on the right here, you can see I'm holding $1 billion because each one is one D-Wave chip. Is a quantum annealer. On the back there, you can see a particular cell of 8 qubits. Now, you can see the lines are 4 horizontal lines. Those are the 4 qubit. And then you have 4 vertical lines. Those are the 4 qubits. So 4 and 4 interconnect together into one cell. So there's a limited connectivity. One is connected to like 4 to 6. Neighbors. So even though you have 5,000 qubits now in an advantage system of D-Wave, it probably still going to be very limited when you try to have to combine and clone different qubits together to make the connectivity to fit your problem. It's using a superconducting ring. So each line is actually a ring, and using the magnetic field, you will direct the undecisive current direction, and then make the superposition. Okay, so in the Rose's law, and then Kolkov's law and Navin's law. So this is different from the previous. So every so often, so as you can see, 2013 now is 10 years, going from 512 qubit to 5,000 plus qubit for D-Wave. Similarly, IBM and different systems also improve. I was speaking in India, and this is the slide that I would like to focus on the energy and the space and part, the efficiency for quantum. Even if quantum is not faster or quantum is not doing all the solutions now, I'm still sold for quantum for these reasons. For the system cost, the refrigerator might cost about $15 million. But it might use 10 years because you can still put, so as you can see right now, the Vantage system is still the same size refrigerator. So I calculated about 47 cents per second to solve problem. And how many problems can you solve? Right now we are running about 27 milliseconds to 38 milliseconds for the mega Sudoku problem. So 100 milliseconds is a one eye blink. So if it's 20 milliseconds to solve your problem, is 5 problems can be solved in very fast eye blink. You know, if you blink slower, it's like 500 milliseconds. All right, so the electricity for the refrigerator is 25 kilowatt, okay? So like the frontier is in the megawatts, but this is kilowatts. So it's basically $0 for that, you know, 1/50th of a blink of eye. Over here, the size, actually, when it's stabilized, it only needs 3 feet by 3 feet. So 9 square feet. Right now, it's about 9 feet by 9 feet because you need 4 people to work in it. Okay. Okay, so this is India. Okay, so this is the platform that we're using. So AWS Blackit, D-Wave Ocean, IBM Qiskit, so any one of you can use. IonQ is giving $10,000 credit. Then there's the Qubit and the Strange Work I find very useful. Okay, so that's Prenet is from Qubit, the creator, and this is Steve and Andrew and Adam. They are for Strange Work. They are from Texas A&M graduate. I'm very proud of them. So most of the project we're working on the left, on right, I show the quantum annealing project and quantum computing project. Over here on the right, it should have also some kind of a Grover's algorithm, Shor's algorithm over there, but I didn't put it because everybody knows about that. But here I'm thinking, everybody spends so much effort trying to correct error. Maybe we can also embrace error because some of machine learning is actually can be enriched by error. What is machine learning? You divide the sample into different regions, and the most tricky part, the accuracy, is lying on the border regions of the near misses or the cases that's hard to differentiate. Okay, so we need to put up the data set to be able, so maybe error can be, so maybe some of you want to work with me, we can try to enrich the data set and see if we can get better learning. On the left here is what I focus on, okay, because right now it's already in production. Now quantum computing is probably another 10 years. As you can know that I'm in my winter of my research, so I would like to focus more on the quantum annealing. I told my students they have to learn everything. But Dr. Sinclair of Harvard Medical School has changing everything. He's thinking we can live reverse aging. That is bad news. Now I have to learn both, right? Okay. All right, so we do Sugaku. My approach is called AT-Mapper using A-star algorithm, which is to optimize the mapping between hardware and software and topology well. Traveling salesman's problem, we call refactoring as the sequencing. The sampling cyber-shake. For example, in each location of the earthquake, we have to simulate 10 million cases scenario to find the worst case so that we can market that point for the resident to know how much strong a house you need to build here and how much insurance you need to buy. And do we want to put a nuclear power plant here in this location, or do we want to put, you know, some military base in this location or something important? So those are the things that we have to produce. But with the Grover search, supposedly you can search the sampling space. You can find that drug. You can find that material for superconducting, and you don't have to worry about energy problem, right? You can find that material that won't deteriorate, won't create space debris. We can find that material biocompatible to make these replacement parts. So there's a lot of sampling. We can find that worst case even better than random sampling in our current Chpc earthquake project. Instead of 10 million case, we can do 10,000 better case. We already get 1,000 times faster without spending any money or energy. Okay? We can use it for nature conservation, for weather, for resource. We can use it to study the longevity, the epigenetic, right? So in Africa here, I'm coming back to the root where the human origin is. In Africa, where you have so many different minerals and you have the plants, you have harsh environment, and it's where the survival gene can kick off. Okay, so there's other plant that will have potential, like the tea we're drinking. I'm drinking very hard on all the tea. We have what's called rooibos, right? Okay, or berberine. Okay. All right, so this is the IBM. They just 21 hours ago. I was trying to watch the YouTube last night, but the power is at 2 a.m. The power is not there. Okay, so this is, they just announced the IBM, instead of one wedding cake, now it's 3. Okay, so you have 3 wedding cake upside down, and it's composable. So you can kind of make it like a Lego pieces, compose different system. There's a modular system called utility scale, system called IBM Quantum System 2. Remember the D-Wave System 2? Right, this is System 2 of quantum. Okay, and then they have, this is what it looks like, and this is going to be their data center. This is not here yet. This is just the dream. Okay, so they are going also from 133 qubit system. Now they're going to condo is 1,000 plus qubit, and they are shooting for 5,000 qubit next year. They say by the end of next year. Okay. Okay, so I talk about the platform. There's two places. One is called Qubit. I'm interested for my student to start using, because in this one system you can do AI and different quantum platform all in one place. You can do IonQ Rigetti, you can do GPU, you can do IBM Qiskit, NVIDIA, Quantum CUDA, Python. Okay, so you can do all these different things just in one platform, and it looked very fluid. I saw the. So another one we have access now is StrangeWork. So StrangeWork is created by Texas A&M graduates, and here again we have access to the Amazon bracket. They give us some credit, and also we have access to the vector annealing from NEC. We can also access vector annealing from Texas A&M. Right now they have like $25 million grant. They have 2 clusters. They actually have 6 clusters, but 2 are the most important one. The Access cluster has a vector engine and vector annealing license now that we can use. This is the rector, and also the Dr. Huang is behind the scene. This Sherry is the one organized all the training events, and Dr. Lu is the director for the Texas A&M. So it's even harder now for the supercomputing people that you have to use the composable hardware, because how do you know you have this much task, and which part should go to FPGA, which part should go to next silicon? I don't even know what next silicon is, right? And which one is gonna go to the GPU, and which one is gonna go to the CPU, and which one is gonna go to what? Okay, so you have to, so right now they're using a liquid fabric. Okay, so these are the different resources. Even the memory module you can select. So you can select the different resources to use for your application. But the tricky part is how you select, right? And how you partition it. These are from the training slide of vector annealing that I have great hope with. So you talk about typically when you do the quantum annealing, you have to, or digital annealing, you have to design your constraint into qubit, okay? The first machine free us from having to do long division by hand. The second machine is going to free us from having to do any tweaking, okay? I just have to ask the right question. I just have to set the constraint. And in a split second of blinking your eye, you get 10,000 different feasible solutions that meet your constraint. Okay, so this is a little history about quantum at the NEC. NEC actually has their own D-Wave-like quantum annealer, but it's not public, it's R&D. But they do have vector annealing available to use, and also they have the vector engine. They also have the gate system, which they kind of embarrassed as one of the director in NEC says, because 20 years ago, NEC led the world in quantum. But 20 years later, Canadian, Chinese, US, and many other countries are ahead. So now they started to try to collaborate. As you can see, 1999, they demonstrated the first solid-state qubit in a Nature magazine, okay? So now they are starting to catch up. Now in 2020, they start to collaborate with D-Wave. So they are already in production is this digital annealing, vector annealing they use is every morning they have to spend the company is a huge company. Even I saw in another room, the projector is from NEC. So when this different company, they buy the NEC system, they will have to ship the parts to that office to install. Then they have to send the technician that's capable to do that particular installation to that location. Just to schedule this logistic of the parts and the people, the technician, it will take 2 hours a day to optimize. Now with digital vector annealing, they can do it in 12 minutes, okay? Oh, by the way, I didn't mention, one of the examples of D-Wave, or maybe I'll show more, but one of the examples of D-Wave is liquidation. So in Canadian banks, every day they say they have 75 huge deposit and withdraw. So they just do traveling salesman's problem to sequence these 75 transactions to minimize the asset they have to liquidate to make the negative balance. By using D-Wave, they are able to save $500 million a day with this 75 transactions, just reordering it. And how much does it cost to run D-Wave? 200 runs of 20 milliseconds. Each run costs $20, okay? So with $4,000 cost of accessing D-Wave cloud, they can save $500 million. So it's very amazing. So for NEC, using their own vector annealing, they are able to go from 10 times, from 120 minutes to 12 minutes. So they save about 25% of the cost of the company by cutting 2 hours out of 8 hours a day, okay? The vector annealing, vector engine, each card can do equivalent of 100,000 qubit, completely connected. Remember I talked about D-Wave, you have limitation of connectivity? It's only run 200 watts, which is a quarter of the other GPUs. with 8 cards you can put together, is capable of 300,000 qubits, okay? So it's very amazing. So we are very happy that we're going to be using it. Right now for D-Wave, when we do 25 cube Sudoku, we already belong D-Wave. When we do 49, so right now we can only do 49 by 49 2D Sudoku. Here is one of my students working on this. Is the beam packing problem. So this is a standard example for D-Wave optimization. Now I'm thinking, can I put one of this custom topology, your job, and put it in a supercomputing cluster? Another way to think about partitioning your workflow into threads is the shuttle bus pickup problem, right? So they say you have 3 shuttle buses, okay? You have the green, blue, and red, and you're going to pick up the jobs, okay? So that means you can take this workflow and cut it into 3 threads, okay? The blue, green, red for 3 different workers. And what is the best way to partition it? Okay, so we can apply this quantum annealing, and this is another paint shop, so it's a typical exercise. You can improve 20 times just by switching the paint color at the manufacturing of automobile. Okay, so this is my student did the 3D Sudoku. So over there's Mario at the right-hand side lower corner. He's the one just got snatched by John Schaaf, and John Schaaf is the U.S. leader, CTO for the NERSC Energy. He was our boss at the computer science department of the Berkeley lab. So Mario is an undergraduate student. Now last summer he worked for Berkeley lab, and then at the end of summer he's become the full-time. Okay, so you can see here there's a cubo right there on the left corner that describe the constraint, and you just run the sampling. Then you can get the problem solved. This is another AI project. It's kind of like bio-inspired. So my student used the GPU, used the evolutionary design, and try to design a manufacturable. So it's like 3 projects in one of a heat sink for a chip. And as turned out, it looked like a Christmas tree. So nature is very organic. So we're not trying to make a Christmas tree or make it nature, but it's automatically making nature. These are other projects in cancer detection. There's a prostate ultrasound in the middle. They are like cells counting. The breast cancer on the right, and then there are like thresholding, sliding. The brain tumor on the left. So we do some different research on it. This is the earthquake project. This is the quantum refactoring that I'm talking about, reordering the 9 instructions here to improve the performance. So I'm trying to work on is to find a synergy between quantum and HPC instead of competing between quantum and HPC. Last summer I was working for Oak Ridge National Lab. That's my collaborator there. So we were dancing, right? In a whole SC of 14,000 people, not too many people dancing. But then I was taking picture at the last day reception, and I found my collaborator was dancing. So I had to dance with him. It turned out that my collaborator and I were the only dancers in SC. But I did not know before we collaborate we like to dance. But dancing is prerequisite for the robotics program we have, and singing is prerequisite for the digital signal processing. Now, obviously, my collaborator, Raphael, he's a work leader on the workflow initiative. So I guess to be good at workflow, you need a little bit of dancing, right? So those are the posters that we did at the Berkeley Lab summer project, where we compare the quantum low balanced job placement with my low imbalance AI job placement. All right, so here you can see 90% of time is 0, 1 hop. When that on the left is a robot elbow task graph. Then you select these 9 different candidates. And after you select, there are 4 of them has the best performance. And then you can further improve by growing or pruning nodes to create custom topology shape. So Dr. Burko is my collaborator in Berkeley Lab, and her project called Tiger, and I am, our mascot is the hawk. So we are having the hawk add wing to the tiger. When I was working for the DOE National Lab, I had to learn all this. So the fine-grained inter-process communication, the workload placement and execution, scale and heterogeneity, individual application, custom application workflow, underlying resource and platform, less movement, better power consumption, resource partitioning, and these are all my project trying to answer. About 3-4 decades ago, this is my dissertation, where I defined the software hardware mapping and scheduling. There I have horizontal mapping and vertical mapping, vertical migration. So migrate the computation to lower like FPGA and different system, microcode, and horizontally partition to the parallel workers. Dr. Burko, my collaborator in Berkeley Lab, has this example to describe the Tiger mapper. Again, it's a low-balanced job placement, worker assignment in the cluster. On the left there, that's a task graph of 11 tasks. On the right here is a 4 processor connected in a ring, in a box. Now, I want you to remember this 11 software task graph and the 4 hardware processor worker. So this is the Tiger system using D-Wave, digital hybrid. So these are the people we were competing for the Berkeley Lab. And so I think only me got selected that year, but there's another person was delaying from previous year. So I was there. That's the Dr. John Schaaf, the ISC General Chair, my boss, and that's Dr. Burko, and beautiful view of the Golden Gate Bridge and the VIP in the guest house. So this is when I was talking to Dr. Burko first time. So what we try to do is take the hardware and software together and make a schedule. As you can see here, there are 4 workers, the 3 color. The last process is not used, so I grayed it out. So this 11 tasks will be done in the 3 processor. Now, 35 years apart, Dr. Burko has 11 tasks mapping onto 4 processor. And he was not even born when I did this, right? Because 11 tasks mapping on 4 processor. So I found my twin, right? So it's very much. Okay. So I guess I have to face forward because I'm taking up your time. Okay. So we run a lot of quantum annealing and AI. So these are the result. So I'm going to show you the comparison here. So with the Tiger and the AT mapper, so you can see the total hop is 26. AT mapper, the total hop is 8. Okay, so the number of processor used is 4, and the number of processor used for Tiger is 6. Okay, so again, Tiger is low balancing, and I'm doing low imbalancing. You can see the difference there. And the reason I love Tiger is because it's quantum. Mine is just AI, so I want to make it quantum to be in one eye blink. Okay, so here we do some comparison. That's our team. This is just some project on my students. So I just play a video here. So the student I mentored. So here you can do the superconducting material, again, using the sampling. You can, in the future, hopefully we can use Grover's algorithm to find the unobtainium. This is space radiation, some of the space project we did. These are some of my students. So this is my high school girlfriend. She's the head of DOE science office. So she's in charge of all 17 labs. I was just visiting one lab. This is my high school girlfriend, and she just gave you $10,000 discount on your cell phone. So she is the one that cut the cord for us in the cell phone. So Dr. Teresa Mun. While she was giving a talk on the Taiwan University commencement, my other girlfriend graduated with a PhD in physics in Taiwan University, and she is the chief in the defense and national security for Taiwan. So my other friend, my roommate in college, is the mother of EDA, was the R&D director for the last 27 years, or 29 years of Cadence. This is my other classmate at the college. So she is the CEO for the Samsung chips for the RF chips. I have some interview over there. All right, are you quantum? Okay. So at the end, this is my family. So I would like to conclude with Mick Conway's game of life. If you are only one person doing quantum HPC, you die, right? If you have 3 people around you doing quantum AI HPC, you become alive, okay? All right, so let's all work together on this journey, and then we'll do great things and go places. Thank you for your attention, for joining my talk this morning.
So today I want to talk to you guys about a very important scientific problem, which is about data democratization and some of the main challenges. So in this presentation, I want to state that the contents were done by myself and hundreds of my collaborators. In fact, it was interesting listening to last talk. My PhD was in general relativity. John Towns, he was developing the biconjugate gradient method during this time. John Schauf, he was the person doing the visualization. So all of us have evolved, and all of us are seeing that data is very important. I was asked to have just one slide about Frontier. I'm at Oak Ridge. For those who don't know, Oak Ridge is in this small spot in the US where you see the star over here. Just have to get used to the pointer here. So Oak Ridge is in a very scenic place. We have the tradition of, since I've been to Oak Ridge for 18 years, of having some of the world's fastest systems. Frontier is what I would say is an evolution what we have been doing at Oak Ridge. So when I came to Oak Ridge, it was the start of the leadership class computing facilities. There were 2 that were standing out. There was at Argonne and Oak Ridge. At the time, Oak Ridge was deciding to go for what we call fat nodes, so more computing power per node. Argonne was thin nodes. Now, this was playing out during what we call the exascale computing project. For those who don't know, it's a project which is just ending. It was hundreds of billions of dollars in this project. The outcome, and thanks to Cray, we have some wonderful systems. They're all GPU enabled. Argonne didn't really go for the thin node because there were some issues with Phi, and Phi was discontinued, and ultimately we went for GPUs. the systems for exascale were supposed to be less than 20-something megawatts. Oak Ridge has a system which is 25 megawatts. The way we like to think of power is roughly $1 million per megawatt per year. So it's quite a bit of money. So when we have a 25 megawatt system, it's $25 million for power. Argonne has a system which, how many megawatts?
Oh, I can't tell you the number.
Okay, I can say 60 plus megawatts. So it's about power, and we heard that, but it's about power, computing. So in Oak Ridge, what we see is Frontier is 1.6 exaflops. It's not that many cabinets. So what we're doing is we're making denser and denser computing. So when you're going to have these nodes, these cabinets, you have to reinforce the floor now. So these things are very, very heavy, very dense. So we're making things smaller. That makes it interesting. All the systems in the US now, which have Cray, are all going for Slingshot. The thing that I like about Slingshot that was presented to me a long time ago is it lets you connect from some experiment directly getting that data into memory. And that was something which is very important, as you'll see in my talk. So what we have is on this AMD processors, AMD GPUs, and in terms of the storage, we are going larger and larger, but the bandwidth to storage is not getting much. So on Titan, which was our first GPU system, what you'll see is that we had something which was capable of 1 terabyte per second, and on Frontier, we have almost 10 terabytes per second. So when you look at the computing power from 27 petaflops to 1.6 exaflops, the bandwidth to storage is not increasing. Now, let's talk about data democratization. So this is an ongoing process of enabling everybody in an organization, or in science you can think of all the climate researchers, to enable them to have access. And you want them not just to have data access, which is what many people talk, but it's also how do you deal with this when the data sizes are growing? So this is a major challenge. And how do you think of this in terms of the entire workflow, the analysis pieces, all the things that you have to do? And you have to have trust in this data. And this is some major challenge. So where this goes and where this gets something which is very important to me is I deal with people in many smaller institutions. And I would say that not that many people have Frontier, on their organization. Here, what do you guys have? Like Happy, what's your biggest supercomputer? It's a little smaller, we'll say. So if you're going to have large data, and I'll go over this, you're going to have a challenge. The other interesting thing that you'll find out is that when most people do analysis from Frontier, they use their laptop. So you think they have the fastest computer in the world, they generate petabytes of data, and they'll use their laptop to do the analysis, which means that they're missing so much important content. But we have to enable this. This is just a slide saying we know the V's. So for those who have understood the V's that we say for big data, there's volume, there's velocity, there's variety, and there's value. These systems that produce it, whether it's a facility like SKA, I mainly work with SKA low. I love to be able to talk to people here about SKA mid. There's huge amounts of data. So for SKA low, it's roughly 360 petabytes of data a year, every year. So you have to be able to think about the importance of this and the value of this, and you have to optimize. I also work with CERN, and that's a lot of data. So in all these cases, lots of data. So I want to ask some questions, and I want to be very simplistic because I don't know how much basic math that you have. And what I want to say is that when people want to deal with data, we have to stop this thing about saying we want to move and duplicate a file. And I say it because I deal with so many experiments and simulations which generate very large data. For example, a fusion simulation I work with generates roughly 10 petabytes of data per day when they run on Frontier. So if I have 10 days of that, which is just a measly 100 petabytes, do you guys have enough disk storage? No. If you're going to replicate the data, like in SKA, you're going to move 360 petabytes of files. But what we know is that people want to get what's inside the files, what we call the variables, or you can say data sets, or places. For example, in the room, you may want to say, I only want the data in the center of the room. Or you may think of this in queries. I only want to get temperature where the pressure is high. So queries become important. Variables become important. Things evolve in time, or what we call steps. How do you get this? So how can we think of that? It's not files. It's the information content. And if we can think of this in certainty, we want to think of things in a simple way. How do we say if we're going to move a petabyte to the laptop, and Happy probably has a petabyte of RAM in his laptop, close, right? You have about a petabyte? Oh, okay, so at least you have a few hundred terabytes of RAM or storage. Well, no, that's right, you don't. So what if you can only get data which is 90% accurate? We could quantify the error bounds. And you only want to get some variables, not every variable. You can then take the petabyte and reduce that to maybe gigabytes, which then you could handle. So you can just look at it in smaller regions. So these are the things. And we also have to guarantee sustainability. So this is the traditional way. Ian Foster is a researcher at Argonne. I'm on certain projects with him. And the typical thing has always been, we're going to move a bunch of files from one place to the other, and we're going to do it fast. And if you think about this, it's like what I tell my students. If I gave you a bunch of magazines and said, your job is to move them from that place to that place, and if every day I doubled, you're going to get a bunch of friends because you're smart, right? But if I keep doubling, you won't have enough friends, and it's going to be hard. The person over there is supposed to do something. So one day you're going to get smart and say, what are you doing with these? And they said, we only want to get the magazines which have the cover of a woman scientist on it. Well, you're probably going to do that before you move it, and then move just the ones. That's going to give the other person a faster job to deal with them. That's going to give the movement to be faster. So you want to start to understand, what do you want to do with the data? And in terms of files, don't just move files, move the information. That reduces this cost. This is the Earth System, the Earth Science Grid Federation, and you'll see they have a web interface, and it's nice. Anyone can go to this, and they can move all the files. So I did a little experiment, and I tried to do this, and for one thing I was interested in, it was only like 12 terabytes of data, which, of course, I don't have 12 terabytes on my laptop. We know Happy does. 12 terabytes of disk, right? Okay, I doubt it. Okay, so you have a problem. So you have to think what's in there. And depending upon what you're looking, you can then think, I'm not moving files, I'm thinking information. So along the way, one of the things that I did, and this is a PowerPoint problem, this should animate in there, but one of the things I did was I started saying, can we do things similar like MPI, but with self-describing data? You want to publish data, you want to subscribe. You want to get data, you want to push data. So we want to think about dealing with data in terms of a service-oriented architecture. So Amazon, and everyone in the room heard of Amazon here probably. It's a very big company around the world. One of the things that Jeff Bezos made famous was that they said all the interfaces to our data is going to be well-defined. In other words, they talked about a service-oriented architecture. So about 15 years ago, I set off saying, can we get a service-oriented architecture for high-performance computing? And you have to think of performance. And what it allows, though, is that I can have data being published and subscribed, and it can go to storage, or I can just have some application which just reads in this. So in other words, think of things in Mother Nature. If we want to take your temperature, you don't have to change your entire body. You stick a probe or a thermometer, we measure your temperature. But in a simulation, if you want to do in situ, it's always been modify your code, do these things so we can get temperature coming out in situ. So we wanted to say, just publish. If you publish and no one subscribes, no problem. You don't pay a cost. So this is what we set off to do. We created something called Adios. It's used all over the world. I've created the framework and the architecture. Jay Lofstead, who I don't see Jay here, maybe he's here, or maybe he's seeing the animals, but it's okay. Jay was the student that came from Georgia Tech that sat in my office, and we bounced around these ideas. We came with the algorithms and the initial framework, and through the exascale computing project, we threw away all the code. We rewrote it in C++, made it much more sustainable, and in performance, so many codes. This is just a small amount of code. Some of these you may have heard about, some maybe not, but we get terabytes per second writing and reading from storage. This was a paradigm shift for codes, and then we allowed more in situ. Now we have things GPU aware, GPU direct, because when you have GPUs, how do you get more optimal? So again, it's performance, because if you're going to have something and you really want to get people to use it and work with the largest data, you need the performance. So I want to get into, this is my history in one slide. When I was a PhD student in general relativity, I was working on these things called Cray YMPs. I was a few years after this. We had this thing called an SSD. Now, most people think SSDs are new. But yes, they were back in the late 80s, early 90s. And what we had is a hierarchy of storage. Cray computers were great, and this was well matched. You had a gigaflop processor with gigabytes per second to storage. These were the great days of computing. And we heard about already their simulator, and that was actually instrumental for creating the exascale computing project and the whole leadership computing, because the USA saw that the dominance of supercomputing was going to be taken over. So that is where I started over in Oak Ridge. We had many systems, but when you look at all the evolution here, storage is the thing that has not evolved, the bandwidth and even the capacity. So this creates a lot of problems. So to get into this, just some cases that I work with. So everyone here is probably knowledgeable about fusion energy. It's a very popular topic now, and you'll see this is changing. What's happening is that what we're trying to do is we're trying to think about how do we recreate what's happening on the sun to Earth. So we start thinking of the effects. Many codes are built. This is what we call a particle and cell code. Very simple. You think of the six-dimensional space. And here what we understand is that when electrons are moving, ions are moving, they're roughly moving in circles. So you can go from six-dimensional to five-dimensional. And then you could simulate the motion of the particles and map that to a mesh. That's called particle and cell. Well, they generate a lot of data. And if you do, and you want to write all the physics in our simulations at the time, all right, this is not pointing anymore, but that's okay. It's 70 petabytes of data per day. How do you deal with it? Well, we can come up with a particle distribution function. Think of it as a PDF. And what we can do is in the extra 2 dimensions, so again, classical physics, I love it, but I'm a physicist. What we have is space, and we have velocity, or we have, again, you have x and mv, momentum, or energy. So from this, that's how we get 6 dimensions, which is in all physics. But because we're going in a circle, we can average that out, go to 5 dimensions, map the particles in velocity space with the probability distribution function, go to 5D, and now we have that reduction. But that's still roughly a terabyte of data per step. That still gets us to petabytes of data in a day. We still need to reduce it. That's part of our job, along with then saying, can we visualize? Can we understand? So then this is where we want to use our technologies. And in this case, actually in the visualization, we had a new form of physics that we saw in a simulation, which was then validated from several experiments. And it's called homoclinic tangles. This is some work that I'm doing with GE Aerospace. And in GE Aerospace, they started making the largest runs on Frontier and Summit. All of a sudden, they had data that were terabytes per step of output. They were running with a technology called CGNS that was then, that was then built with HDF5. They were taking 2,700 seconds per step. Using Adios, we reduced that time to 5.6 seconds. So that's a huge decrease, especially when you write hundreds of steps. Now they're working with us on data reduction. Because if you can write data quickly, and now we have all that data, now they have more data they can deal with. They want to get that data back in GE headquarters. So reduction, compression becomes important. E3SM, that is the Earth System Modeling Framework, so that is their climate framework. We've worked with them. That was this year's Gordon Bell. And on the ultra high resolution case, which won the Gordon Bell, it's called SCREAM, and I can't remember what the S is, but it's Cloud Resolving Earth Atmosphere Model. I forgot what the S is. But we were able to reduce their time. These are essentially these are powers of 2. So we were able to get 4 times faster in the I/O. But ultimately, it was how do we really get that data written so we can do the analysis? And I want to get into a little bit of that in a second. All right, audio is not working again. That's okay. I'll go through this. This is Michael Boosman. He's from Helmholtz Institute. They're trying to build these miniature lasers which target tumors. So instead of thinking about chemotherapy, they're thinking, can we use these small lasers that act like beat waves? They're creating simulations, it's okay. I can talk through every video. So they're taking these simulations, it's particle and cell, it's huge amounts of data. And what they're being able to do is validate their simulations. Now what they're trying to say is, but the problem is, it's just so much data. They were a Gordon Bell nomination at some year. We worked with them. But now what they're doing, and if I said one more thing that I hope would be a theme for next year for you guys, digital twins. How do we recreate this? And what we're doing is we're creating these digital twins of these fully coupled systems. Data is a central element of this. And in a digital twin, you have to think from what your digital twin is, how does that come back to the simulations, the Chpc simulations, and how does that go to the experiment? So I think you talked about this also. These are the big things that we see in the next 10 years, right? So this is critically important. And we do want to think about working together on these. This is combustion, Jackie Chen. And again, the performance graph, this pointer works on and off. But that's okay. Again, increasing the bandwidth. But what she's doing is she's trying to take these huge data sets. And from the huge data sets, can we put them in a place so everyone has access? Well, I'll show a little video later, but from 1.5 terabytes of data per step, thousands of steps, and putting them all on a web server. Is that easy? No. It's like, forget it. So reduction is important. I/O speeds, workflows become important. The analysis, visualization of this data becomes important. So these are all things which we need to do. There's another code. Does anyone know a code, spec FEM? It's a very famous code used the world. They use it for seismology. It's your own Trump is the main researcher from Princeton. I won't show the video because audio is not working. But what I would say is that they generate huge amounts of data again. Okay, it works now. 7.5 petabytes. This is Summit. That is in a single workflow step. So this is a very important code. I would say for Cray, this is one of the bigger codes, I'm assuming. And these things are doing these inverse problems. And I/O becomes a very important thing. And you have to do this properly. And what it shows is no I/O was 94 seconds. So run the code for one step or just 50 tasks, 94 seconds. And we were able to, at the time, reduce it to 156 seconds with I/O. But it's a lot of data. So I/O is not free. But that's how you do your science. Again, this is the video. And really the thing is, when you start scaling these codes, there's a lot mathematically you have to do in your algorithms of how you scale them. Because it's running essentially as an ensemble of runs in these events, you run them together, so the network between each ensemble is there, but you can go further and further. So all we're trying to do is to make sure that the data, the science that can come out, can be good. Now, let me go forward. This is SKA. Now, again, we don't have audio, but I will let this go a little bit. Maybe if I can, I don't know how to forward the time of the video. But basically, this is SKA. They're talking about how important SKA is. And SKA definitely has a big data problem. Again, I think Cray's interested in this. They chose from the focus on adios for their output because of many things, but performance is one of the things and sustainability is another. So we were then subject, we led the Gordon Bell Prize with the scientists at Perth. And the thing is, we had to really think about how to reduce the I/O by orders of magnitude. For the sake of time, I will speed that up. So now, and again, I like to see this from probably, some people will say, we're evolving from single executables to running these multiple executables, which are ensembles. They're parallel, they're independent, but you're putting it together to gain more about the uncertainty. But as we evolve, as AI comes and you're integrating AI with HPC simulations, there's a lot of coupling that goes on. And the technologies that we use to couple have to be very efficient and have to work across all the systems in the world. And then we're creating the digital twins that come from this that interact. And then the data that comes from this, we need to make available to the community. So if we're going to do that, some of the things, it needs to be self-describing. Now, does anyone know what self-describing data means? It's a quiet room, so I'll say it. But self-describing means that what you want to be able to do is when you see some numbers, there's some additional data which tells you, oh, that's temperature. Temperature is a three-dimensional array. Temperature has units. So there's more information contained. We call it in the metadata. Additionally, what we'd like to be able to know is what's the minimum value of it? What's the maximum value? Without going through all the data. So things have to be fast, and it has to work in all tiers. So Summit was one of the first systems which had what we call node local NVMe on each node. So that was so that people can write faster. Now again, if someone asked the question on that machine, how many people use that instead of the parallel file system? What would your guess be?
Very few.
Yeah, less than 2. No, lower. You're a vendor. You want to think that, but that was IBM, so. No, but now Frontier comes and we have the same thing. And it's difficult. Now, there's a lot of reasons that I won't get into, but we want to think, how do we go through these storage tiers? How do you work with data, whether it's coming from streams or files? How do you then have the ability that you can capture this information, query this information, and make it available to all the applications? Adios, I mentioned, I'll just say some of the things that we're interested in. How do you query? So for example, if we're getting all the sensors in this room, there's temperature, but there's also like the wind velocity. You kind of want to know it because if it was really hot or cold here, someone might want to know, where is the pressure in a certain region, or where is the wind blowing, or people commonly think vorticity. Vorticity is just simple. It's the curl. If you know your vector calculus, it's just simple. But it's a vector operation, not of the data you saved. So these advanced queries become important because if you're dealing with large data, you don't want to read it, you don't want to move the files, you just want to get the information. And now, given that we're looking at new things like in terms of storage, we have compute on storage, we're getting compute in networking. They're talking about GPUs in networking or smaller ones. This allows us to then use that to reduce what's being moved, either through a query or through these reduction techniques. In situ processing, for in situ, we want to say, all you're trying to say is, I want to get some data, I want to move some data, and you want to think of things in steps or transactions. So this will make it easier. And when we talk about data democratization, when more people are doing in situ, you need to understand what happened. That provenance has to be there. And then we don't care if it's files or streams. This allows us to work then on these services. So Kitware, which is a visualization company, they also make CMake, if you're familiar. Now CMake is becoming a more standard way of building codes. And what it does now is what they've done is they've built something called ParaView. That is a parallel visualization system. To do in situ, they've had Catalyst. And what they did very recently, which they have, if you have a code that has adios, don't change the code. And then it then just interfaces directly with Catalyst. And now you can do traditional in-memory in situ. Or you can do things when you're running your simulation. It's again with the temperature probe. I just fire up ParaView. It connects to the code. The code never knows. And now you're doing in situ viz, and you can interact with ParaView, and the code's not aware, and you don't slow down the code. So these are the paradigm shifts that we're looking. But the next is in reduction. And in reduction, what we're trying to say is, can we now have the data and then refactor? And what that means is, if you think of the data in this room, one might think of, I have a bunch of processes generating, but like you have data and it goes, and you have what we call logic contiguous. The data goes and it's given one way. But when we think of video, and I think we're using Zoom for this, in Zoom they use wavelets. When you have less bandwidth, it looks worse. But has anyone here used Zoom in a video conference? I'm sure someone here has. Okay, I see someone shaking, good. You ever notice, like, when your network goes, what do you normally do? You turn off the video, right? You have to think, what a stupid technology. If it really did this properly, it would actually degrade the video so much that it's only the audio. Always make sure the audio is prioritized. So this refactoring says, how do you prioritize the data? So what we looked at was a technology called multigrid. Now multigrid was very nice in terms of a nice mathematical framework to solve elliptic partial differential equations, and what we call the order n methods. So biconjugate gradient was not. That meant the more your problem grows, the smaller it goes. You know, I started 15 minutes late. Okay, hold on. So what I'm trying to say is that this is a mathematical technique which has guaranteed mathematical error bounds to not just refactor the data, but could quantify the errors in these quantities of interest. And this is just a simple mathematical proof, which then was put into an algorithm. And from here, in order to then use this, you have to optimize this. And when you think of reduction, our entire community was all lost. They've talked reduction with MPI. It only got reinvigorated because of GPUs, which can do these complex calculations very fast. And these were just graphs of showing how fast and how well this works. So this is just showing that we can take data, and this is 15 gigabytes of data per GPU. There were 6 GPUs on a node. So these are terabytes of data that you can then reduce it and then write it to storage in just a few seconds. So this is a game changer for us. And that's why, again, having this on the network becomes important. And then you could quantify errors again, and I'll just focus on this slide due to timing. And now this is looking at climate data. There's several variables that are important for cyclone tracking and atmospheric rivers. We had a little bet with the climate scientists that we could reduce the output but increase the accuracy of cyclone prediction. So they were outputting data every 6 hours, and that's, in real world hours. We got them to output it in every hour and reduced it. And what you'll see in this graph is essentially what we can do is reduce this and get more accuracy. What? To this? Oh, I meant to point on laser pointer. Sorry. So here, what we're showing is that there are more advanced techniques than what we call decimation. Instead of outputting just every 6 hours, output every hour, but then use these mathematical frameworks that can really guarantee you accuracy, so then they can get more accurate data for their analysis and have less data output, which then helps to share this data. We've been applying this with SKA. We have a paper coming out with SKA where we can do this to get 0.2 sigma, which means that the error in the reduction is less than instrument noise, with a 20x reduction now. So instead of 360 petabytes a year, it's 20x smaller. That's savings of millions of dollars per year. And then think of sharing. It makes it so much less. GE is also, they've been working with us. They're actually coming to Oak Ridge on Monday, where I found I have to present. And they're trying to work more with us because of the importance of this. So I'm trying to get close to finish, and this is close, where we're enabling so many more things as we try to speed up the I/O, make it then it's ubiquitous between streaming versus files, having reductions that's now part of this I/O pipeline that can guarantee accuracy. This was the second to last slide, and this was just showing it's not a complete product, but what we're trying to show is that this is S3D data. It's impossible for you guys to read them back. What we're showing is it's 1.5 terabytes of data per step. And 1.5 terabytes for most people is large. But you don't want to move the data to your laptop because you don't have 1.5 terabytes free for just one step. So we also have what we call a derived variable. It's called magnitude, if you can read it. And now what we're trying to say is there's nothing in the variable. What we do is we save certain statistics on it, but we don't save the actual data for that variable. So when you're on your laptop, you can just use, in this case, Adios, to get what variable. This is over on Oak Ridge. This is just a laptop at home. And what we want to show is that we can run our Python scripts. Don't modify the way we're working. It's the same way as if we were on Oak Ridge. The connection right now is manual between the systems, but that will be automated. So what we're trying to say is you can run with your Python notebook. Just get the data the normal way you would, like it was in files. You just have the metadata. The metadata knows where the actual data is, and you get variables that you want. And then when you run your Python script, this is just showing, this is running with the Windows subsystem. So this is the Windows file browser. And the Python script is just creating images of these 2D slices. And then instead of doing that, you can go further, and then you can just grab 3D volumes. You can grab queries of these derived quantities. And due to lack of time, I'll just go, this is my last slide. If you're going to democratize data, it's not files. It's the analysis. It's having the metadata. So what you want to do is you want to make it findable, addressable, interoperable, all the things that they say fair. But you need to think of this for large. So you have to think of accuracy. In other words, if you're sitting here in South Africa on a laptop, how do you access petabytes of data, but maybe less accuracy or a smaller piece of the space than if you went over to, say, Oak Ridge, where you can operate on everything. And this becomes very important because if you can then guarantee the errors, if you're seeing something that looks interesting, like I have a picture from one of the nights and it looks like there's a UFO, and that's because I'm incompetent and the camera blur of the sun, so it looks funny. But if someone was going to analyze and they said, wow, there's a UFO in South Africa, that's not having enough context. So you need that metadata, and you need to know how that data was reduced. So again, it comes to, if you're going to do science, errors are important. So I'll just end with questions.